our original supersymmetry operator was del by del theta was it plus I theta bar del by del t, and q bar was equal to del by del theta bar plus I theta del by del t. Okay, and we defined the set of right. So we define the set of two thetas, theta 1 and theta 2, and correspondingly a set of two theta bars, theta 1 bar and theta 2. And then we had q1 bar, q1 and q2 operators. We had q1 bar and q2 bar operators. Just used by these formulae, but everywhere there's a theta and a theta, we put a 1 or a 2 index. And as straightforward as you can get. And then we argued that the supersymmetry algebra was qi, qj bar is equal to twice the Hamiltonian delta ij, and everything else was zero. Every other commutator was zero. So at the level of this kind of algebra, we're doing absolutely nothing. Okay? It's just trivial extension of what we've done. Okay. So, now, what was sort of a little non-trivial was this. As you remember in the last class, we discussed that if we took a superfield which was a function of arbitrary function of theta 1, theta 2, theta 1 bar, theta 2 bar, the general expansion of that superfield would have 16 bosonic or fermionic, 16 component field components in it. Okay, and 16 sounded like sort of like an unpleasantly large number. Some of them might turn out to be auxiliary fields, but many will not. And then we are automatically, committing to dealing with a theory with a very large number of fields. That sounds like very complicated. So instead of dealing with the most general possible superfield, we decided to try to find some reduced set of superfields. Some reduced set of superfields that don't have all those 16 components. But the problem with doing that in a completely random way is if you put some constraint on a superfield. In general, if you act with the supersymmetry operator on that constraint, it will take you outside the constraint class. Okay? So the whole point of using superfields, namely to have a good representation of the supersymmetry algebra, will be lost. On the other hand, if you put a sensible constraint, namely one that commutes with the supersymmetry or anti-commutes appropriately with the supersymmetry algebra, you don't have this problem. So the constraint we hit upon was demanding d bar of theta 1 on phi is equal to d bar of theta 2 on phi is equal to 0. Because the d bar operators commute with all four supersymmetry operators. Okay, these constraints are those that commute with supersymmetry. And so the constraint field before and after variation, if you start with a field that is constrained like this, acting with q on it will continue to give you a field that is constrained. Simply because we can take q through the d bar up to a minus sign, and if it was 0 before, it's 0 after. Right? So why not do? Oh, we could do it. This is a convention. D bar. Yeah. Just a convention. Why not both? In fact, as we will see, the fields that we get by doing this are complex. And a complex conjugate of a field which obeys d bar on theta phi is equal to 0 will obey d on phi is equal to 0. So in some sense we are going to do both. Okay? In fact, we will need both as a need. Okay? Fine. So let me make that argument immediately. This business about being complex. You remember, and somebody should correct me if I'm getting the practice of I know, when we expanded our fields, we had x is equal to x plus I theta psi plus I theta bar chi, or psi bar, we said to call chi psi bar, plus I theta theta bar. Right? This was our expansion. Now, you remember, up to this point, our theta and theta bar were just psi and psi bar. Okay? But there was no particular notion of complex conjugation in that notation. However, of course, it's not a coincidence we call it psi and psi bar. There is some notion, there is a sense in which psi and psi bar are complex conjugates of each other. And what is that sense? The sense is that psi mapped to the operator psi, when we quantize it, psi mapped to the operator sigma minus, whereas psi bar mapped to the operator sigma plus. And as operators, sigma minus and sigma plus were Hermitian conjugates of each other. Okay? So if you want to keep track of things that are real in an operator sense, in our superfield language, we might want to develop a notion of complex conjugation for these anti-commuting numbers, so that the numbers that correspond to Hermitian operators would become complex conjugates of each other. That's a convenient thing to do. Okay? So let's define the notion of complex conjugation. The notion of complex conjugation is that the complex conjugate of psi is equal to psi bar. And similarly, we define the complex conjugate of theta is equal to theta. But now x here was a real field, so we want this whole thing to be real. So now let's complex conjugate this guy. If we just do a simple complex conjugation, of course we will get a minus sign. Okay? So this field will not turn out to be real, right? Because this will map minus this. So part of our notion of complex conjugation, part of the rules we develop, is the following. This is a convenient set of rules. Okay? Just rules we invent so as to keep this field, to make this field real. The rule is that if I take complex conjugate of alpha, beta, but these are two complex, two anti-commuting numbers, this is beta star alpha star. Complex conjugate is accompanied by interchanging order. Okay? And it's inspired by the fact that these are really keeping track of Hermitian operators. And we know that the Hermitian conjugate of AB is beta A. So this is what inspires this rule. Okay, but anyway, at the moment we just need that this rule. With this rule, this becomes a real field. Okay? So now we've got a notion of reality, and we have a nice real field. Our original expansion, our field that we chose was a real superfield. Yes?
So it should come directly from the property of the anti-commuting number, because product of two anti-commuting numbers should be a real number.
Product of two. First, the product of two anti-commuting numbers. It's an even number, it's not a real number.
It's even in the sense that
It's an even number, but how do you know whether it's real or not? You need it. You need it. Okay, it's a number. But whether it's complex or real, how do you know?
yeah, that is fine, but let's say we try to find the model of that. Model meaning complex number. Yeah.
What do you mean by complex? It's not a number. It's a product of two anti-commuting numbers. See, an anti-commuting number can be represented as an operator on some matrix space. Product of two operators is not identity.
We can define, let's say, some norm or whatever in that.
You can define, but I'm saying that you originally were saying that there was an automatic notion of complex conjugation. That is not there.
Here you are defining the complex conjugation.
Yeah, and we're doing it very similarly to what you want, because you see these things are like operators. And we're defining the complex conjugation to mimic hermiticity properties of operators. Okay, so it's more or less what you're saying, but not for numbers, but for operators. Okay, excellent. So let's keep going. Okay, so let's keep going. I'm waiting to get back to 1866. Okay, so let's keep going. Yeah. Okay.
What is the reality for the last term?
The reality for the last term is also real because theta bar interchange. I picks up a minus.
I picks up a minus.
And then theta bar goes to theta. So f is real. So all these things are real. X is real, psi is real, psi bar is real. Okay? Yeah. Excellent. That means another way to incorporate this complex conjugation rule we wanted f to be real. Because the equations of motion set f to be real. Is implement this condition.
theta bar complex conjugate will again be theta bar, right? So then I becomes minus I, so that will be problem.
You're very right. Can somebody remember what our solution for F was? What was our solution for F? Did it have an I in it?
It was minus I only.
Minus IW, sorry. So I'm sorry I gave you the wrong answer. F was imaginary. Yeah, because our solution was minus IW, W was the superpotential. Thank you, Chitra. Thank you for correcting me. So I said two wrong things that cancelled each other out. Now we say two right things that continue to cancel. Okay, so Chitra correctly pointed out that when we take the complex conjugation, we get minus I theta times F. So with this convention, F had better be imaginary, thank you. But it was imaginary by the equations of motion. So that was a consistency. Thank you. Okay. Excellent. So let us keep going. So we want to set this condition. And we want to know how to implement this. Now, I want clearly a phi that is a function only of theta, right. I want to find a set of quantities here. I want to find a set of quantities here that will obey this condition. So, you know what I want to do, it's like this. Suppose I have two variables, x and y, and I know that del by del x of my function is 0, then I know the functions are only a function of y. Okay, but if I knew something more complicated, let's say del by del x plus x del by del y of the function is equal to 0, I can still often find a variable that it's only a function of, right? Because I try to make some change of variables to make that combination del by del that variable, that something at constant something else, and then it's only a function of that constant something else. So that's the kind of game we're going to play. Okay, so we're going to try to find a set of variables. Okay, we're going to try to find a set of variables that that automatically obey this condition. Okay, first let's look at the variable theta 1 and theta 2. So let's say theta 1. Okay, we want to know, does theta 1 obey this condition? Well, what's this? This is del by del theta. Of course, when we do theta 2, it obeys it. Okay, so we will do del by del theta 2 plus I times del by del t on theta 1. Del by del t on theta 1 is 0. What? Theta, thank you. Del by del t on theta 1 is 0, and del by del, sorry, I wanted del by del theta bar and theta, because we've got del bar. So, minus, thank you. Minus, thank you. Okay, so I want a del bar on theta, I want to check whether del bar on theta 1 is 0, but that's clearly true because del by del bar, del by del theta bar of theta 1 is 0, and del by del t of theta 1 is 0. Just the variables that appear in the derivatives are never theta 1, similarly for theta 2. So clearly, theta 1 and theta 2 obey our conditions. So if I take something to be a function of just theta 1 and theta 2, it will obey this condition. Okay, but that can't be enough, because originally we had 5 variables. We had time, theta 1, theta 2, theta 1 bar, theta 2 bar, and we have 2 differential conditions. That should be enough to eliminate 2 variables. We should be left with a third one. So we should be left with something like time. But time by itself doesn't quite work, right? Because if we take time, we'll get I theta 1 acting on t. So let's try something a little more creative. How about looking at the variable tau, which is t, and then we'll fix up plus minus I theta 1 bar plus I theta 2 bar. Let's look at this variable tau. Okay, let's look at what we get from the del by del t. Say we do it with the d1 bar operator. Okay,
The d1 bar operator clearly kills this guy. It acts on t by giving you a minus I theta 1 bar. Right? Because the theta 1 gives this. But it acts on, it acts on t giving you a minus I theta 1 bar because d by d t and there's a minus I theta 1 bar.
No bar.
Theta 1, thank you, no bar. Thank you, theta 1. Theta, thank you. Minus I theta 1, this is from here. Then there is del by del theta 1 bar, okay, which gives us plus minus I theta 1. Okay, so if we choose the minus sign, this now gives 0. Okay, so if we and clearly the same algebra holds for theta 2. What's the difference? So we've got a nice variable here, tau. This variable tau obeys the condition that any function made that d bar on tau is equal to 0, whether it's d bar 1 or d bar 2. Is this clear? Fantastic. So now we've got the most general solution to our chirality condition. These equations that d bars annihilate fields is called a chirality condition. Okay? The most general solution to a chirality condition is simply this. It's that phi is equal to some arbitrary function of tau, theta 1 and theta 2. Very much like we would do with real variables. The chain rule of, product rule, the Leibniz rule tells us that this will always work for differentiation. Right? This will always be annihilated. We've got the right number of variables, so it's the most general solution. Okay? So this condition, which at first looked a bit complicated because this d bar operator mixed time derivatives and theta derivatives, is actually a simple condition. Tells you that phi is an unrestricted field, not now of tau, which you think of as, roughly speaking, a bosonic variable. Well, certainly an even variable, but roughly speaking, sort of like a commuting variable. And two anti-commuting numbers. This makes the expansion of this superfield as complicated as X was, or as simple as X was, in our earlier expansion. Okay? So, this is a nice trick to play. So, we will try to make a theory built out of chiral superfields. Okay. So, let's look at the expansion, the most general expansion of this chiral superfield.
Is this the most general one because it has all theta, 1 and t?
You can of course make more restricted classes, but you will need all of them if you want it to be invariant under supersymmetry. Supersymmetry will act on, suppose you said, for instance, that there was no theta 2 bar, there was no theta 2 term. Then by acting with supersymmetry on a field without a theta 2, you will produce a field with a theta 2.
No, I'm saying this is the most general one.
This is the most general, yes, most general solution to this equation. Just, right. Yeah, so most general, as you can prove, just like you do for real numbers. You make a change of variables to 5 variables. And with these new variables, this is d by d one variable and d by d other variable is equal to 0. Okay? So, yeah. So,
we can also add like some containing the spatial part of the space.
space, there's no space, there's quantum mechanics. Right? Good. When we go to quantum field theory, all of these things will have to be modified, not very deeply, but just to be consistent with Lorentz invariance. The simplicity we have here is there's no Lorentz invariance to deal with. Okay, and because we're not dealing with, because we don't have to worry about Lorentz invariance, no indices to play around with, so everything is very easy. That's why we're doing these expansions first. Okay, well, it's a very similar, as most of you know. This is a sort of retro course, right? Because most of you are familiar with supersymmetric field theories. So, as most of you know, when we study 4-dimensional field theories, we have a very similar chiral expansion, very similar in that case you call that thing, that tau y mu. T is replaced by x mu, and then there are some thetas, but the thetas then have to carry some spinor indices to make up a vector index. Okay, it's basically the same thing, but with a few more bells and whistles to be consistent with Lorentz invariance. Right now we're trying to avoid those complications till we have to get them. Excellent. So we've got this thing. Now let's write down the most general expansion of our field phi. Okay, so I don't know, we should have some, let's call the superfield, you know, some fancy capital Greek letter. Okay, so phi is a function of, so what I'm now going to do is to expand it as follows. I'm going to expand it as just in the theta 1 and theta 2 expansion. So let's say first I expand it as phi of tau plus I, and let me call this theta 1 psi 1 plus I theta 2 psi 2 plus I theta 1 theta 2 f. We may drop some of these i's later on if that proves to be convenient. They are functions of tau, but they're not real fields. Then capital phi is not a real field, not a real superfield. Okay? It's not a real superfield, as is obvious, because if you do a complex conjugation, this theta 1 will change to a theta 1 bar. Okay? So now, because as a superfield it's not real, it is natural to treat this bosonic component also as not being real, as being complex. So now we're dealing with the theory of a complex boson and these two fermions. Complex fermions, psi 1 and psi 2, whose complex conjugates will appear in the expansion of of phi star. So phi star, f is also complex. Yes, f is also complex. Phi star is equal to little phi star tau. Okay, and now we will get minus but plus because of the I. So plus I theta 1 bar psi 1 bar. I'm not writing it's a function of tau. Everything is a function of tau.
Should not that be phi of tau star because it is complex because of tau?
Phi is complex because of presence of tau.
Initially we had this function of time.
Yes.
It could be a complex function of tau. Yeah, and it can be real.
Yes.
It can be combined possibilities.
Yes. It's a good point. I mean, I was going to say that this is going to be real, but it looks complex, right? It looks. That's an interesting point. Schur points out that the way I've defined it, tau is not a real variable. Tau is not a real variable, right? Yeah, I think you're right. Tau, because when we take the complex conjugate of this, as Chintan pointed out, we get theta 1 bar, but this becomes minus. In fact, let us, as a check on what Schur points out, thank you, as a check on what he points out, let's also solve the equations d theta 1 and d theta 2. I'll try to find the tau-like variable that obeys the equation d theta 1 rather than d bar theta 1 is equal to 0. Okay? So d theta 1, right. So if I do d theta 1, I will, from the d by d theta, sorry, from the we get minus I theta 1 bar. Okay, so let me put the conjecture. The conjecture is that it's that I want to check that t plus I theta 1 bar plus I theta 2 bar is equal to 0. I want to check this. Okay, So we have d by d theta. Okay, so d by d theta 1, the time derivative gives us plus I theta 1 bar. Minus, thank you, minus I theta 1 bar. And then the space derivative gives us plus I theta 1 bar. So if you want to find the, okay, so you want to find the variable that is annihilated not by d bar but by d, then that, as Shoaib correctly pointed out, is not tau but tau star. So he is absolutely correct. We have tau star here. So everything now is a function of tau star. So I won't write it. Okay. So we get plus theta 1 bar psi 1 bar plus I theta 2 bar psi 2 bar, everything function of tau star. Thank you, Shoaib.
In this case, what allows the possibility of the function small phi to be a complex function of tau?
What do you mean what allows it? What do you mean? I don't understand the question.
In previous case, we had x and x was real. It was real function of t,
Right.
not a complex function.
It was a,
This phi can be a complex
so
function.
because you see the superfield by nature cannot be real. Because when you take the complex conjugate of theta 1, it becomes theta 1 bar. So it can't be that it's a real superfield. So every component then can be in general complex. Right? It's just a complex superfield by its very nature. A real superfield would have to have democratic expansion in theta 1 and theta 1 bar. But this is not democratic. Right? So this is tau star, function of tau star. And here let's also do this. So we get minus I theta 1 bar theta 2 bar f star. But there was an I. Okay?
Does that if function matters?
What?
Is it if only function of t?
Isn't f effectively only a function of t? And unless, no, but doesn't matter. So Schumann's point is that you just multiply out f. When you expand out, there is there's always a common theta 1 bar. So in f, he's completely right. The fact that it's tau rather than t does not matter. In principle, it's tau star, but it doesn't matter. Which one? Last one is a plus sign. Did I get it wrong? So I got minus. Oh, you're right. Thank you. Thank you. Okay. So we've got a chiral superfield. Its complex conjugate is what's called an anti-chiral superfield. How do we know it's anti-chiral? Well, we've just checked. It obeys the condition d theta on phi star is equal to 0. Because it's a function of theta bar, theta 1 bar, theta 2 bar, and tau star. Right? So this complex conjugate doesn't obey the same condition as we had before, but it obeys another equally good condition. This is what you were asking at the beginning of the class, Nikhil. Okay, so great. So now we've got these two superfields in our hand, and we want to use them to build supersymmetric Lagrangians. Well, one thing we can do as usual is the following. Okay, let's try various things.
Those phi and these phi are same, right? That's a capital phi, right? On which we apply the condition.
Yeah, this was some abstract field. Yeah, but right, the same phi. Yes, thank you. Okay, now, so let us try some to build some supersymmetric Lagrangians. Well, we already know one rule, right? One rule is that if I write d theta 1, d theta 2, d theta 1 bar, d theta 2 bar, and write down any superfield, by S is any superfield, this thing will turn out to be supersymmetric. Why was that? Because the supersymmetry variation always has either a d by d theta, which then kills it because there are 4 d by d thetas here, or it has a d by dt, which doesn't kill it by Fermionic integration, but kills it because d by dt is a total time derivative. So up to a total derivative, supersymmetry operators always kill any such Lagrangian. Okay, so the first thing you might ask is, what if I put here just a function of just a chiral superfield? It needn't be phi itself, it could be phi to the 10, some function of chiral superfield. Remember, if phi is chiral, A and B are chiral, then A times B is also chiral by the Leibniz rule, because d theta bar on AB is d theta bar on A times B plus minus A times d theta bar on B. Since both of them are chiral, both of them are 0. Okay? So once I've given you a chiral superfield, I can get any other chiral superfield I want by taking any function of it. Okay? But whatever that function of it is, it has its own expansion like this. Okay? So the first thing I might think of is putting a chiral superfield here and performing the integral. Okay? Let's see what I get. So suppose I choose S to be phi. As you understand, phi need not be the elementary field of a problem. It could be phi to the 10. For this algebra, it doesn't matter. Right? It has its own expansion in that form. Okay. Now, what we need here is terms with, terms with 4 thetas in order to get in order to get this clicking. So let's first look at what we get from phi. At first sight, you might think, okay, this is just going to be 0, because where are the thetas? But that's not obviously true, because tau is not t. Okay? So what we're supposed to do is to take tau and take the tau dependence and Taylor expand it. Okay? So what we will get is phi of t, that of course gives 0. Okay, plus phi prime of t times minus I theta 1 bar minus let's take a minus I outside, theta 1 bar plus theta 2 bar. This also gives 0 because there are only 2 thetas and we need 4. Okay, and then plus we will get plus minus I, the whole thing squared by 2, and then theta 1 bar plus theta 2 bar square, and this of course multiplies phi double, we should call this dot and phi double dot because it's time derivatives, phi double dot of t. This term here has a term that is non-zero, but notice that it's multiplying phi double dot of t. Phi double dot of t is a total derivative of phi dot, and so this term gives you a total derivative. Okay? Total derivatives don't give you interesting dynamics in Lagrangians, so we're dropping that. Yes?
At the end point, this should vanish, right?
What?
At the end point, this should vanish.
Sorry, what? That's a comment or I didn't understand.
No,
See.
at the end point, when you take the variation, the end point should vanish, right?
The endpoint should vanish. So you're saying that even though it's a total derivative, why are you regarding it as trivial? That's your question?
Yeah, because for phi it's fine, because at boundary delta phi is 0, we take that to be the boundary relations. For how we...
Any term that's a total derivative will not contribute to the equations of motion. Will only contribute, it's not just the variation. The value of the action itself will be completely determined by endpoints. Okay, such thing define basically trivial dynamics, doesn't tell you what path to take in the middle. Okay, anything that's total derivative at the moment we're going to regard as not contributing to dynamics.
It will not contribute to the expectation value.
It will not contribute to classical equations of motion. It will, in the end, it's true that if you have some term that is non-total derivative and you add something like this to it, it might in the end contribute in some interesting way to some path integrals or something like that. Okay? But at the moment we're looking for something a little more elementary. We're looking for something kinetic term and things like that. Certainly not going to give that. Okay? At the moment we're going to drop all total derivatives. Come back to that question at some point. Okay. Now what about if you take the psi 1 and psi 2 and expand that? Okay, here it's sort of immediately clear. Because you have to get 4 thetas. There's already 1 theta, so you can get either 3 thetas or 5. So that's not going to contribute. What about the f guy? Well, the f guy could once again, actually f is also clear, because this comes with theta 1, theta 2. So any expansion term here just gives you 0, as Schumann pointed out earlier on, because every expansion term has either a theta 1 or a theta 2. Okay? So it's just 0 up to the total derivative in phi that we're ignoring. So what we've understood is that if we take a chiral superfield and integrate over 4 thetas, we get a trivial Lagrangian. Okay? Integrating over 4 thetas here of a chiral superfield gives us a trivial Lagrangian. It would be supersymmetric, but it's boring. It's just the total derivative, effectively what we're calling 0 at the moment. Okay, so now how do we get interesting physics? Starting with the chiral superfield, if we can't just make functions of chiral superfields and integrate them over 4 thetas. We can take derivatives? Now that won't help, because if we take d bar derivatives, that just gives us 0, and we take d derivatives, that leaves it chiral, because d bar and d. Yeah. So that's not helping. So what we're going to have to do is one of 2 things. First, remember that we have in the game I said it like it was a big puzzle, but actually what I'm saying is something very stupid. When we take a complex field and we try to make a Lagrangian, we never take the complex field to the power 10. Yeah, exactly. We want complex field times complex conjugate to get a real Lagrangian. So obviously this wasn't going to work, because we were trying to, a Lagrangian should be a real number. We were looking at some complex thing. So one thing we can try to do is to take phi bar, or some function of phi bar. Now this will work, because phi is chiral, but phi bar is anti-chiral, and the product phi bar is neither chiral nor anti-chiral. So that will be exactly like the kind of situation we had with one supersymmetry. Okay? This will give us something non-zero, and we will work out what it gives us in a little bit. Okay? So this is going to work, that's fine. Okay. The other thing we could do, however, is something more interesting and more creative, and that's this. It's to look at the integral over half of superspace, d theta 1, d theta 2 of phi. This in general is non-zero and continues to be supersymmetric, as I will now argue for you. Okay? Now you see, had phi not been a chiral superfield, this quantity you could still write down, but would not in general give you a supersymmetric Lagrangian. Okay? Why not? The argument that integrating over 4 thetas gave you a supersymmetric Lagrangian was that each of the q's acting on the field, once you integrate with the 4 thetas, gives you 0 or a total derivative. Okay? And the reason was that the d by d theta term is 0 because we already have a d by d theta in the integral, and d by d theta squared is 0. And then the d by dt term gave you a total derivative. But here, if we took just a general superfield here, that argument works for d by d theta 1 and d by d theta 2, so it works for q1 and q2, but it doesn't work for q1 bar and q2 bar, because the d by d theta bar term in q1 bar and q2 bar could act on this and give you something non-zero. Okay, so this thing here is not in general supersymmetric if phi is a general superfield. However, I want to argue that when phi is a chiral superfield, this thing here is supersymmetric. By which I mean that when I act with any of the supersymmetry operators on it, I get either 0 or a total derivative in time. Okay? Let's make the argument. First, the argument for q1 and q2 is the same as before. That's d by d theta 1, d by d theta 2. That's d by d theta 1, d by d theta 2. So the same argument. If you've got a d by d theta 1, that's 0. And if you've got a d by dt, well, it's a time derivative. Okay? What about the argument for d by d theta bar? For q theta bar, q bar. Well, you see, the argument is actually very similar. Once again, the theta bar, the theta d by dt is 0 because it's a time derivative. So we only have to worry about the d by d theta bar. Clear? Now, d by d theta bar is not 0 acting on phi, but the only way it gives you something non-zero is by the chain rule, because phi is a function of tau. So from the chain rule, what you get is a derivative of phi. And so whatever you get from d by d theta bar is a total derivative in time. Is this clear? So because the theta bar dependencies are inside this t minus I theta 1 bar plus theta 2 bar. You could, if you want, just expand it out. Put in that expansion. And because the theta bar derivatives will only come because you've expanded each of those fields in tau bar, in tau, and that expansion will involve derivatives of the fields in time. An integral of a total derivative. I mean, so variation is always total derivative. Therefore, the action is supersymmetric. Simple argument. Okay? So now we've got two kinds of terms we can use with these chiral superfields to make supersymmetric actions. The first is any function of d theta 1, d theta 2 times some chiral superfield, but we want the action to be real, so we'll add plus complex conjugate. Okay? We'll add plus d theta 1 d bar d theta 2 bar phi bar. This may be minus when we think about it hard enough. This phi is capital phi, yes.
Sir, what about epoch tau term?
What?
Epoch tau term.
Yes.
If we expand that, we will get some f of t only. And if we integrate out, we will just get f of t.
But then we get 0 from the d by d theta bars, because that's a function only of theta 1, theta 2.
We are applying d bar.
Right? We are applying d bar. So there's no way out of it. If you act with the d by d theta bar, it can only act on the tau. So you always get a derivative. All clear? Okay, excellent. So this is one kind of term that we can use. And the other kind of thing that we can write is d theta 1, d theta 2, d theta 1 bar, d theta 2 bar times some g of phi bar phi. Or let's call it phi, I don't know, phi bar phi. Okay? This plus w of phi, any function here, plus w star of phi star will be the most general Lagrangian we can write down using chiral superfields. That is supersymmetric. Is this clear? It's the general chiral superfield, and therefore here we want to make the most general chiral superfield we can, therefore we put a function of it. Okay? And it's true that here, yeah, here also we put another function of phi fiber. Nothing more we can do. Okay? Of course we can try to do, sorry, we could try to do more by adding like time derivatives and so on. Okay, or d thetas. But we will see that if we want a two derivative action, this is what we are forced to do. All other things will give us four and higher derivatives. Okay? So it's sort of interesting. The interesting thing is that the kinetic term, as you will see, the kinetic term comes from here. The kinetic term is a term entirely without derivatives. You remember when we were looking at theories with two supercharges, we built a kinetic term out of a d and a d bar, d theta x, d theta bar x. Felt right? Kinetic terms have derivatives. Now we're going to get a kinetic term with no derivatives. But it will be kinetic because this thing is a function of tau rather than t. And tau has its expansion, and that expansion will involve derivatives. Okay? So let's see how this works. Yeah, today's class will be just largely boring algebra. Sorry for that. We'll get to the more interesting mathematics next class.
When we apply this transformation, why are we not considering the change in the measure of the guitar?
What?
When we apply this transformation, why are we not considering the change of measure in guitar?
Okay, good question. Why are we not considering change?
Typical operator, we haven't defined what the supersymmetric transformations are, or x and theta, right?
Yeah. What we are trying to do at the moment is to write down actions that are supersymmetrically invariant. This will do that, right? There's no measure in an action.
How do you know that if we, let's say, apply t, it will pass through these measures?
What measure? In the path integral measure?
Okay, changing field, but we haven't defined what the supersymmetric transformation is.
Wait, what measure are you doing? The change in of suppose I've got some field x. Del q on x is defined to be q acting on superfield x.
That is fine. Right now you are checking that when we are applying this, on the Lagrangian it will be something, right?
On the Lagrangian, yes. So the action itself will be supersymmetrically invariant up to total derivatives. Then there is a question of potential anomalies due to path integral measure in the quantum theory. But that's not the thing. We are trying to construct supersymmetrically invariant actions. So there's no issue of measure. We just have to check that under the variable transformation, the action changes at most up to a total derivative. Okay? The question of demonstrating that supersymmetry, that there exists a non-perturbative regulation scheme that preserves supersymmetry.
Sir, I'm asking how are we changing the fields?
This way. What?
We are changing the fields, how are we changing the, let's say, space-time variables, those things?
No change in space-time variables. These are
Changing the fields,
just the fields.
So it will not change the measure.
No, there's, you meant measure like dx.
Yeah,
Yeah, this is what we mean by the supersymmetry transformation, right? And we have demonstrated under this supersymmetry transformation, it's invariant. This q induces a change on all the components of x, or all the components of phi, like we saw for the two supersymmetry case, right? You understand? It's nothing more complicated than that. I misinterpreted your question. Sorry. What? The path integral measure is very interesting. In the case of quantum mechanics, of course, since we can do Hamiltonian language, there's no issue, right? We got the supersymmetry operators, we got the Hamiltonian. In the case of quantum mechanics, there's no issue. It just became classical geometry. So mathematician could prove supersymmetric because of d and d star and so on. In the case of quantum field theories, it's interesting. The question of finding a non-perturbative regulation scheme that preserves supersymmetry, I'm not sure there is a clear answer to that. Of course, we all believe it exists. In perturbation theory, some sort of dimensional regularization works well. non-perturbatively, is there a proof that it is possible to find a non-perturbative regulator that preserves supersymmetry? I'm not even sure that such a. Let me quote Seiberg when I asked him this question. Maybe not on tape. Hey, let me quote him anyway. When I asked him this question as a student, he's a great practitioner of supersymmetry. He said, no, it's true that there does not exist a proof that there is a non-perturbative regulator for supersymmetry. And it's true that if somebody finds a theorem that there cannot exist one, I will fall, but I will take many people with me. I think that's the situation. It's believed here. Okay.
In this case, we are not constructing action with terms like super derivative terms because the d phi is 0. But we have q and q bar. They are also to some extent super derivatives, but with time reversed problem. So we can use terms like q.
You can't use terms like q. Well, you should only use the d and d bar because you want in the Lagrangian only terms that commute with the supersymmetry operators. Okay, so as to make the operator on general superfield transform like a superfield. Remember, this is the same argument we had earlier. Now, but you're right, we could have used d thetas on phi. Nothing stopped us from using d thetas on phi. We could use that. But that, as I will try to explain to you, would give us an action that is higher order in derivatives. If we want an action that is second order in derivatives and no more, this already does it. Okay, so hang on. Okay, so the first thing I'm going to try to understand, so as I said, I'm sorry, this is going to be a long, boring algebraic class. But if you think this is a lot of algebra, wait till you get to higher dimensions. Okay. 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 So the first thing we're going to do is to try to take the action integral. Now we should make some convention. So last time I think we did d theta and d theta bar as an integral measure. So let's do this. D theta 1, d theta 2, d theta 1 bar, d theta 2 bar. Let's say this is our integral measure, and I'm going to take the simplest possible term, which is phi bar phi. Okay? And I'm going to try to see what comes out of this. We could take more complicated functions than this, but the story is going to be like in the one dimension, like the two supercharge case. When we have one variable, any more complicated function can be reabsorbed by field redefinition, because that more complicated function will encode the metric of the space. And in one dimension spaces, metrics are sort of simple, as we will see. Whereas in the higher dimensional case, taking more general functions will be key. Right now we're in one complex dimension, so we just stick to this case. We will move to the higher dimensional case in the next class.
G was phi phi.
What?
Phi comma phi. That general action.
Yes.
It is phi phi.
It's some function of phi phi.
Okay. And that is the simplest you can write.
This is the simplest, linear. Okay. What I have in mind is I want something quadratic. Let's first be easy and then we'll. Okay, so now what do we have to do? So let's expand. D theta 1, d theta 1 bar, 2, d theta 1 bar, d theta 2 bar. And now I'm just brute force expanding. Okay. So I get phi plus I theta 1 psi 1 plus I theta 2 psi 2 plus I theta 1 theta 2 f, where all of these guys are functions of tau, and then I have phi star. Everything here is a function of tau star. Okay. Please correct me if I'm making mistakes. I theta 1 bar psi 1 bar plus I theta 2 bar psi 2 bar plus I theta 1 bar theta 2 bar f bar. Okay. And I always have to keep in mind that everything here is a function of either tau in the first line or tau star in the second line. Okay. And now I want to pull out all the terms tau star is this variable. It's the complex conjugate of tau. Okay. I want to pull out all the terms that will contribute in the 4 theta expansion. Okay. Now, first thing, let's try to get some sort of systematic. Okay. First, it's clear that we will never have a term which is a fermion times a boson, because that will always have odd numbers of thetas. In the expansion, we always want 4 thetas. So we can get boson times boson or fermion times fermion, and let's look at those two terms independently. So let's first look at boson times boson. Okay. So that was phi plus I theta 1 theta 2 f into phi star plus I theta 1 bar theta 2 bar f star. Okay. Now let us remember also what tau was. Let's write that down. Tau was equal to T minus I theta 1 bar minus I theta 2 bar. Again, please correct me if I'm getting it wrong. Okay. Now let's see. Okay. So first we get terms from phi star. Okay, let's do the easiest ones first. Let's do f star. As Schumann pointed out right at the beginning, in f we never need to expand. Okay, so all terms involving f are relatively easy. So f star is just what we see. What we see is what we get. And in fact, we're in the right order: theta 1, theta 2, theta 1 bar, theta 2 bar. Here you're really going to have to help me. So I'm getting a minus f mod f squared. Okay, great. Okay. Then what about terms involving phi and f star? This is never going to work. Can you see that? Because as soon as we expand phi, there will be at least 1 theta bar, and that will kill this. Okay. Similarly, phi star and f will never work. Okay, what might work is phi and phi bar. Okay, let's see what we get there. So what we're supposed to do is to take this and that and expand both of them and pick out the terms that are 4 thetas. Okay, now we could get a term where at first order in the expansion of this and first order in the expansion of that. We could get a term at second order in the expansion of this and 0th order in the expansion of that, and the other one. Okay, so let's keep them all. Okay, so the first term, let's say the term that is first order in this and first order in that. Okay, so that's phi star dot then minus I into plus I, because the expansion was this and then complex conjugate. Okay, and then theta 1 bar plus theta 2 bar into theta 1 bar plus theta 2 bar. Do you agree? Okay, so that's plus phi dot phi star dot, this is plus, and now we've got the term which is, let's say, this guy with this guy. To make it work, we have to do one flip, and so we get a minus. Similarly, this guy with this guy, we could first take that there, no sign, and the same. So I get minus 2 with a minus 2. Please check. All good? Excellent. Then next, let's take the term where this guy is expanded to second order and this guy is zeroth order. Okay? So because this guy is expanded to second order, there is a half plus half, that's in the Taylor series expansion formula. I squared is minus 1, so there's a minus. There's phi double dot phi star, and then there is theta 1 bar plus theta 2 bar square. Okay, this we've just manipulated. This gave us a factor of minus 2. Okay, so we get, so now the other term is of course symmetrical, so we get minus, so the full answer is minus 2 phi dot star plus phi double dot phi star plus phi star double dot. Okay? And now if we integrate by parts, dropping total derivatives, if we integrate by parts, this picks up a minus sign, this picks up a minus sign. So we get minus 4 phi dot phi star. Okay? So please, this is the kind of thing that can kill us. You guys have to help me. Okay? So final answer we get by expanding that term is minus mod f square minus 4 phi dot phi star dot up to total derivatives. Okay. What is nice about this action? The nice thing about the action is that we've got a kinetic term. We've got a phi dot phi star dot. Even though there were no derivatives in the action we put it. Where did we get it from? We got it from expanding, Taylor expanding tau in t. I mean in thetas. Right? Great. So far so good. A wrong sign, then we'll put a minus sign in the beginning. I mean, we don't, if you remember our last, for the superfield thing, we needed to take minus half d theta phi d theta bar phi. And this we'll also put a minus sign. The whole thing, there has to be a sign so that the whole thing works out. Okay. Right. This we've just done some algebra. So here what we want to do is take minus 1/4 of this if we want standardly normalized things. Okay, yeah, so we could say that minus 1 by 4 of phi bar phi d4 theta is equal to, we've checked, phi star dot phi dot plus mod f square plus mod f square by 4. Okay, great. That's one term in the action. Now let's look at the other term in the action, which is the integral. By the way, if this was the only term in the action, oh sorry, we've forgotten the fermions as well. We have to do the fermions. Let's do it. We're doing the fermions in 2 minutes now. This is the bosonic term, but if this was the only term in the action, the equation of motion will be F is equal to 0. And we just get free bosons. Very similar to if we had the d theta bar, d theta x, d theta bar x, you know, that superfield Lagrangian we wrote down for the 2 supersymmetry action. That also we just got free. But before we do anything else, let's work with the fermions. Okay. So we've got the fermions. Let's go back up. Okay. So what we've got to do is to take I theta psi 1 plus theta 1 psi 1 plus I theta 2 psi 2 into, so now I square is minus 1, so we get minus theta psi 1 plus theta 2 psi 2, theta 1 psi 1 plus theta 2 psi 2 into theta 1 bar psi 1 bar plus theta 2 bar psi 2 bar. And we have to take d4 theta of that. Okay. Now you see these cross terms are never going to click. They're never going to click because this one is a theta 1, 1 theta 1, 1 theta 2. And when we expand tau, we always get either 2 theta 1s, a theta 1 bar, or 2 theta 2s. We are all 4 different theta, so the cross terms will never click. So it's only the direct terms that click. So we only need to worry about minus theta 1, oh, so now we'll have, because I take it through, yeah, plus theta 1 bar, psi 1 bar, plus theta 2 bar, psi 2 bar. Right? So now we can get terms if we expand either of these to first order, because in the expansion of this or that to first order, there is the term which is theta 2 bar, and we can pick that out. So let's look at that term. Okay. So when we expanded psi 1 to first order, let's take that term first. We get theta 1 bar. Then we're only interested in the term that's theta 2 bar. That came with a minus I, theta 2 bar. And we got psi 1 dot psi 1 bar. Okay. Now we put this theta 2 here and this guy here. Okay. Really we should be doing it the other way around, right? Because I had defined my integration as 1 bar 2 bar, and the guy at the end acted first. Let me change that integration because we've been doing it as if we've been picking out the component of theta 1, theta 2, theta 1 bar, theta 2 bar.
But if you do it constantly,
We just have to pick out this component. That's what we mean by integration measure. So let's fix that. Exactly. Yeah. Anyway, so this is what we always do. For d4 theta, we mean pick out this component. Okay. So then we get plus I we get plus I psi 1 dot psi 1 bar, right? Okay, and what about the other term, the term where we expanded psi 1 bar out? Well, that will give us an plus sign here because of the thetas. Okay, that will give us a plus sign here because of the thetas, and no other, and the derivative will be on psi 1 bar dot.
And there will be a minus sign because of the tau star.
That was my plus sign.
And shifting of the derivative, partial.
And the shifting of the derivatives will give us an additional minus sign. So it makes it 2. Okay, so plus 2I psi 1 bar, psi 1 bar, psi 1 bar, psi 1 dot, psi 1 bar dot. Now, the sign is okay, because we always wanted minus. But remember, we had to make this minus here. So let's add to this. Here we get minus half psi 1 dot psi 1 bar. And similarly, of course, minus half psi 2 dot psi 2 bar. Okay, so this is our whole answer up here. I's, thank you. Minus I, minus I. Okay, now we may want to eventually renormalize. If we want this to be standardly normalized and this to be standardly normalized, we'll need to put some square root 2's maybe. We'll think about that. Right now we just work with our conventions and get everything consistent. Then we'll fix to some convenient normalization. Okay, great. So, yes.
In the beginning you said that since we are just working with one superfield, we can take the simplest function and then reabsorb in redefinition.
Yes.
But wouldn't that affect the measure of path integral, because it would be some nonlinear function then?
It could affect the measure of path integral. At the moment, we're just looking at classical actions.
Yeah,
Okay, so then we'll have to worry about that issue, about whether it does or not. In the case of quantum mechanics, we will find the Hamiltonian description of this theorem. It will be some differential operators on a manifold. So we will know the answer to this question. Okay, all these questions become more pressing when you have to do a theory where you cannot just find the Hamiltonian description. Right? So in the case of quantum mechanics, we will work out the answer for every function, and we will find that it is some answer on a manifold, and the changing of the function is just changing variables on that manifold. So since variable changes are true symmetry of differential operations, turns out it's correct. Okay, so there will be no issues in quantum mechanics. Okay, these are all interesting questions, but will not bother us for quantum mechanics. Typically, these measure changes give you local effect, if at all, will give you some local counter terms, which one can then, if it was non-local, it would be a problem. But if it was local, one can reabsorb into some effective shift of the action. Okay, so anyway, in the case of quantum mechanics, we'll never need to worry about this, as we will see a posteriori. Okay, excellent. So we're done with this. Okay, let's hurry up and finish the other term. When we move on to the higher dimensional cases, we won't work out the algebra like. I will give you results. I'll open a paper, read out from a textbook and give you the answer. Because you guys will also get bored. But since this is the first time you're doing all this, we're working it out in detail. I mean, those of you who are not masters in supersymmetry already, it's the first time. Okay. Okay, excellent. Okay. So now we've got the other term. We've got, let's say we want the coefficient of theta 1, theta 2. This is what we mean by d2 theta in W of phi. Okay. So, okay. So, how does this go? Well, W of phi itself looks like it has no thetas. So, everything comes from the expansion of tau, expansion of tau and thetas. Okay. We want 4 thetas, so we need double expansion. Okay. Oh, sorry, we want, sorry, you're right. We want 2 thetas, so we need double expansion, as you said. Okay. So, we want, right, so we want the theta 1, theta 2, and we want a single expansion. Okay. So, we get W, so that's W of phi. Okay. Plus W prime of phi. I need phi in an extended form. You're right. Okay. Yeah. Exactly. 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 So let's open it out as Schumann said. So we've got W of capital phi. Okay. So first we will expand just in the components of phi, and then if necessary later expand in the y expansion. Okay. So this guy was phi plus I theta 1 psi 1 plus I theta 2 psi 2 plus I theta 1 theta 2 f. Okay. Now you see the expansion of these guys in W's is not going to help us. Sorry, expansion of these guys in tau is not going to help us, because every such expansion term has at least one theta bar.
Why that theta bar term will be 0 if you just integrate over theta 1 and theta 2?
Because we are looking at the coefficients of this.
I'm saying given the formula for integral,
Uh-huh.
we are looking at that term. What will happen if we have theta bar?
Yeah.
No. There is no integral over theta bar. But in d theta, that's what we showed. It will be 0, right? When you had 4 theta. But
No.
here we have 2 thetas in theta.
Yeah. Shuman's saying, what about the terms that are just left behind?
Yeah, just Fermionic, as a Fermionic, it's just there.
Yeah.
I can understand it should be real, but
Yeah.
except that there is
No,
no.
no. It will be there. You would have a theta bar term, but all such terms will always come as derivatives.
That is not real. Okay.
Right? Because just expand W. Forget that W is a function of phi. Expand W in chiral expansion. Every time you have a theta bar, that only comes from the time derivative. tau derivative. So anything that involves a theta bar will always come with a total derivative. We just drop it. Okay. So right. So you're right. That's how I should have made the argument. Thank you, Shubhan.
Sorry, but the integral of d theta, integral d theta theta bar is not 0.
What?
Integral d theta theta bar is not 0.
Well, integral no, that's suppose Shuman's point was, suppose you have theta 1, theta 2, theta 1 bar. Now you integrate over theta 1, theta 2. That's left with, what you're left with is theta 1 bar.
But like integral is like a derivative. Right?
Integral is like a derivative, and therefore it's hit this and hit this. But you're left with the theta 1 bar. That was his point. It's true. It's true. You're left with that. Of course, we shouldn't be left with any, something like that would be crazy, right? We wanted a number for the action. So all such terms, the terms Schumann's worried about, but they're all total derivatives. Okay. So ignore them. So basically here, in all these terms, the tau expansion is not important. Tau and t are the same thing. Okay? So what we want to pick out is the term which is theta 1, theta 2. Okay? So we can pick it out either from this guy or from this guy. Okay? So what about this guy? This guy comes only at first order in differentiation. Okay? So we get del W, so I'll call it W prime. W prime times change, but from the first order we get only this term. So that's I times F. Do you agree? You get W prime I W prime F. And then there are the terms which you get.
So W prime is evaluated at small phi.
W prime is evaluated at phi. So W prime of little phi. Phi of t.
The integral is theta 1 theta 2, then it will be minus.
We've decided we are going to choose the terms proportional to theta 1, theta 2. Okay, so then our integral is theta 2, theta 1. That's just our convention. Okay, right. So let's stick to that. Okay, so we get this. And then, well, what about the other guy? Well, the other guy requires us to expand to second order. Right? So that gives plus W double prime by 2 of phi times this thing square. So minus theta 1 psi 1 plus theta 2 psi 2, the whole thing square. Okay, because we have to expand to second order. Okay, and this guy is now, so let's work this out carefully. So this, the first term, so this is theta 1 psi 1 theta 2 psi 2 plus the reverse, which is of course the same, so twice of this, and this will give us plus W prime phi psi 1 psi 2. Okay, so and the factor of 2 goes, so I'm getting plus W prime phi psi 1 psi 2. Please check. This is my final answer.
Just check once for the phi's.
Uh-huh.
Phi has its theta 1, theta 2, theta 1 bar, theta 2 bar inside.
Mm-hmm.
You can have as you had in the previous case.
Right.
And you will have W prime of phi, and then you will have phi prime, then you will have that two terms.
You'll have that, and that will become W dot. Because you have W prime times phi dot.
Okay, sorry, yeah.
by chain rule. That's the easiest way to see it is not to expand as W of phi, but just expand W in its components. Then it's obviously a dot. Okay, so this is now our action, and then finally, okay, so and then we will get plus complex conjugate. Okay. Okay, so we will get, so what is our final action? Our final action, if we started with minus 1 by 4 d4 theta phi bar phi plus d2 theta w plus complex conjugate. Okay. Our final action is giving us phi dot phi star dot plus mod f squared by 4 minus I psi dot psi bar by 2 psi 1 minus I psi 2 dot psi 2 bar by 2, okay, and then plus whatever we got here, plus I w prime of f phi f plus w double prime phi psi 1 psi 2 plus cc. Complex conjugate, because there's a d2, the other term. Yes. Mm-hmm.
There will be something like theta 1, theta 1 by theta 2.
Sorry, what are you expanding? Little phi?
Yeah, little phi.
Little phi, yes, please go on.
There's something like theta 1 by theta 2, theta 2 bar.
Yes.
And the derivative is second derivative.
Yes.
But that's inside W.
That's inside W. You know, the easiest way, it will always work out to a total derivative. The easiest way to think of it is just expand W as a superfield. Call W, little w plus its fermion and so on. Then for that little w, it's clearly a second derivative. Now this will be the second derivative of that little w. So it will be, what you will get is of little w, but little w was w of phi. So you will get w dot, double dot of phi. We open that all out. It will be this. No, but open it out, because you're using chain rule. Right? Okay? See, the easiest way to think of it is not to expand W as a function of phi. Treat W as a superfield. Then clearly it's second derivative of its first bosonic component. But the first bosonic component is W of phi. Therefore it will be second derivative of W of phi. Now, if you expand this out, this will have terms which are phi dot, and a term which is phi double dot. You'll get all those terms when you do it that way, and they'll group up into this. You know that beforehand because you could have just expanded it in terms of the component which was of W. Okay? So doing it your way will also give the answer, but it's a complicated way to do it. Okay? Thank you. Other questions? Excellent. So where were we? So this was our final action. Now, okay. Now, in this action, what are our fields? Well, our fields are f, psi 1, psi 2, its complex conjugates, phi and phi bar. What? W is just some function. It's not a field. Right? But notice that just like in the one supersymmetry case, f here has no time derivatives. So it can just be integrated out by its equations of motion. Doesn't correspond to anything propagating. It's a Lagrange multiplier type thing. Okay, so you integrate it out, and what do we get? Well, let's see. What we get is completing the square from this guy. These factors of 4 are a pain, I have to say. By next class, I will give you more rational normalizations. It's a pain to have this back.
In the definition of the superfield, you could have defined 1 by square root of 2 theta 1 psi 1 by
Exactly, exactly. And maybe a factor of 2 in f.
yes. With every theta 1 there is 1 by square root of
Theta there is a 1 by square root of 2, and that will help us, you say. Okay, let's immediately make Diksha's field redefinition. Okay, so if we do phi is equal to phi plus I theta 1 psi 1 by square root 2 plus I theta 2 psi 2 by square root 2 plus I theta 1 theta 2 by 2 f. Suppose we switch to this, because Diksha from my experience tells us it's a good thing to do. Then all we have to do is wherever we had our old psi was new psi by square root 2. Right, where we had psi earlier, we should be putting psi by square root 2. More. Do we want to put up square root 2 in upstairs? Let me try with it upstairs. Yeah, upstairs. This looks good. Okay, let's make this expansion. Now, every time we had a psi we put an extra square root 2, and every time we had an f, we put an extra 2. So mod f square becomes with a 4, but then that has a 2. That's irritating. I hope we haven't messed up in factors of W.
By 2, if you make
Yeah.
by 2, then it cancels.
Right. And then we say, and
So we will keep that factor because you will be completing square.
what? But there's a complex number. So in complex ones, you don't want the factor of 2. Okay. And then let the action be d2 theta w by 2. Okay. Then we get phi dot phi star dot plus mod f squared minus I psi 1 dot psi 1 bar minus I psi 2 dot psi 2 bar plus I w prime phi f plus w. Lovely, even here it cancels.
Yeah, that complex conjugate, can't it make it with what?
No, when you, because it's complex, it doesn't. Psi 1, psi 2 plus cc. And so now when we complete the square, okay, if we completed the square, we would have made this f f plus I w prime f star plus w prime I w f times f plus I w star prime f. right? This is what we would have done. This would have produced this term, and the complex conjugate term. Minus y, sorry, y. Yes. Minus I W. Okay. And okay. But then this would have been plus W prime squared. So we would have compensated, get a minus W prime phi square, which is good because potentials should appear negatively. Okay. And in addition, we would have this term. So after integrating out, so we should record this somewhere. We are finding f star is equal to minus I W prime phi. F is equal to minus I W prime star phi star. Plus I, thank you. Plus I. And our final Lagrangian is phi dot phi star dot minus I psi 1 dot psi 1 minus I psi 2 dot psi 2 minus W prime phi square, and finally plus W double prime. The I was not there, right? Yeah, double prime phi psi 1 psi 2 plus W double prime star phi star. I hope I've got this order right. Psi 1 bar, psi 2 bar. Or is it? It's probably the other way around. Psi 2 bar, psi 1. Should be complex conjugate. What?
Second and third term.
Sorry.
Second and third terms.
This one and this one? Second term, yes?
Psi 1 dot psi 1 bar.
Thank you. Okay. And this is our final Lagrangian. We'll need this when we discuss supersymmetry transformation properties. Okay. Yeah. I'm going to request somebody, maybe Shuman, to write down the final formulas we found in a nice way on a sheet of paper. We can use that as a starting point for next class. Okay. So we won't do any more algebra this class. We're all sick and tired of it. I certainly am very bored of it. Okay. So what have we finally found from this theory? Okay. What have we, this whole shebag, what has it given us? Well, it's given us a theory of quantum mechanics of a particle moving on the complex plane. Phi and phi bar are the coordinates of that complex plane. Okay. It's got the standard kinetic term on the complex plane, and it's got a potential on the complex plane. The potential is not completely arbitrary, sort of like in the two supercharged case. It's the derivative of a function, mod squared. But it's a little less arbitrary than that case, because it's the derivative of a holomorphic function. W was some nice function which was of variable of phi, which was a complex variable. So it's the derivative of holomorphic function mod squared. A little more structure. And we also have the fermions. Each fermion gives us a two-state system. So we have two two-state systems. So if you want to think of it that way, we've got some 4-component spinner. Right, some 4-component spinner moving on the complex plane in the presence of some potential. Okay? This is what we get from the one-dimensional problem. In the next class, maybe without doing all the gory algebra, we will work out also the multi-dimensional problem, and then we will turn to the physics of this theory. Okay, since we're all bored out of our minds, let's stop here. Okay, of course, questions, comments.
I have a question regarding last class.
Yes.
When you said that when you do the path integral for some field configuration which is like instant term plus fluctuation.
Yes.
Then without any Fermionic operator it will be 0.
Yes.
So is that because let me said, can you explain that?
Can I explain? Yeah.
Anyway, the supersymmetric is supersymmetric, so whatever field configuration we get, whatever fluctuation we get by applying supersymmetry will be 0.
That was the argument. Shall I explain, or is it clear? It's clear. Fine. Yeah. So the point was that there was one fermion mode. You know, the way to think of it is this: when you do a path integral, one way to do it, one way to think of a path integral is to work at the field at each point in time. But it's often more convenient, practically speaking, if you have a Hamiltonian era, to work in the basis of eigenmodes of that Hamiltonian. Okay? So let's say you've got a path integral for the Dirac operator. What is often useful is to solve for the eigenmodes of the Dirac operator, and let your fermionic field be a fermionic coefficient times a bosonic wave function, which is the solution of the Dirac operator, summed over all solutions. And then your fermionic path integral is same as doing a path integral over each of these coefficients. Coefficients of the modes regarded as ordinary fermionic numbers. Now it's not some fancy path integral, they're just ordinary fermionic numbers. Okay? This may be more familiar in the bosonic context. Fourier transform, if it's a free problem, but if you had a potential, it's useful to work in the basis of eigenmodes of that potential. I mean, eigenmodes in the sense of Euclidean eigenmodes. You must have seen that when you're dealing with solitons, or you must have seen this in some context. Right? This is often a convenient way to work, and it's often a better defined way to work. The path integral, often the most convenient definition of the path integral, is to expand in Fourier modes of the free, in the modes of the free problem, and to do the integrals over the numbers that occur behind those expansions. And in fact, even the measure can be controlled that way. If you choose the expansion to be orthonormal, then the measure oftentimes really is just exactly what I said, without any infinite factor to take out.
So in curved spacetime it will be like not
curved spacetime. Even in curved spacetime, you choose the Fourier modes. I mean the eigenmodes of that del square operator. That's what you're saying. Yes, exactly. Okay. Now, so we've got this background instant. We want to expand in the modes of our operator, our kinetic terms for our operators, for our fields, around this instanton background. Okay? Now, because this is supersymmetric, there is one mode that has 0 eigenvalue under the expansion, which means that term does not appear to quadratic order. So the integral over the coefficient of that mode would give you 0, unless you had it explicitly inserted. Like those of you who study string theory with me, we've seen this a lot, right? We've seen this happening a lot, as you know. The C0 modes or the B0 modes, they all come about through this kind of. It's a general way of thinking. So whenever you've got a 0 mode, you need something to saturate that, and this 0 mode is guaranteed from supersymmetry. Okay, excellent question. Any other questions? Okay, so next time we will maybe spend a little time on this one-dimensional problem. When I say one now, I mean one complex. So two-dimensional problem, right? But we'll spend maybe a little time on this two-dimensional problem, And then we'll move on to the multidimensional problem. Look at its physics. I very briefly want to tell you about the theory with 8 supercharges. It's taking a lot of time, all of this. But anyway, I'll at least very briefly tell you about the theory with 8 supercharges. And then let's move on to the quantum field theory. It's 2 or 3 classes I would really like to move beyond quantum mechanics. But okay, let's see. Okay, thank you.